This video covers Trig 1.3 and Pre-Calc 4.3 notes. This will be part 1 of the video. We're going to be dealing with right triangle trigonometry in this section, and so that will lead us to coming up with some formulas for the 6 specific trig functions that we will deal with when we are looking at a right triangle. So first understand that this is a right triangle, and if I want you to find the sine, cosine, and tangent, and then their reciprocal identities, cosecant, secant, and cotangent, we need to know the formulas. Well, this is something that you should have some prior knowledge on. Hopefully you remember from geometry and algebra. You remember this phrase, algebra 2 actually. You remember this phrase, SOHCAHTOA, where sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, tangent is opposite over adjacent. Now when you're dealing with SOHCAHTOA, you have to understand which angle you're going from. So notice that in my triangle they're telling me to specifically go from this angle. So whatever they label as theta is the angle that you typically will go from. Sometimes they'll have an angle measurement already in there for you. And then we label our sides. Across from the theta is the opposite side, so it's opposite of the angle. Across from the right angle is always the hypotenuse, and then by default the last side that you have is the adjacent side. That's the side that's next to the angle, but not the hypotenuse. So now you can use the formula that the sine of theta should be equal to, I like to write the abbreviation over here so I remember what I'm using, the SO part of SOHCAHTOA, opposite over hypotenuse. So in my problem it'd be 4 over the hypotenuse, which I don't know. So before I can actually fill that value in, I need to find that. Way I'm going to find that side is use the fact that this is a right triangle, so I can use Pythagorean theorem. This side has to be C, then it doesn't matter how you label those. I'll label that A and that B. So I'd say 3 squared plus 4 squared equals C squared. This would be 9 plus 16 would be 25. And if I take the square root of that, I end up getting this side to be 5. So I can say then that the formula for the sine then would be 4/5, or the answer for the sine of this triangle. While I have the sine, since I've done the sine, I can find its reciprocal identity pretty easily. I can choose to write it as the reciprocal of the formula. A much easier way to do this is to say that the cosecant is just equal to the reciprocal of the sine. Well, if the sine is 4/5, the reciprocal is then 5/4. Let's take a look at cosine. The formula for cosine, we're looking at the ca part of SOHCAHTOA, would be adjacent over hypotenuse. So the cosine of my angle would be 3 over 5, which would make the secant then of the angle have to be the reciprocal of this, flip the fraction over, 5/3. And finally the tangent is the TOA part, so it's opposite over adjacent. So the tangent of this triangle would be 4 over 3. Cotangent would be the reciprocal, 3 over 4. Another way, if you don't like this phrase SOHCAHTOA, another way that you can memorize this is to write the phrase out. Oscar has a heap of apples. And recognize that the way that this is spelled out is it gives you the OH, so this one together makes sine. Then it gives you the AH for adjacent over hypotenuse. A little bit neater. AH, so that's the cosine portion. And then this gives you the OA, which is the tangent portion. So that's how I remember the phrase, Oscar has a heap of apples. I don't really use SOHCAHTOA. I'll try to use both. I know that most of you have had exposure to this before. You may not have had exposure to Oscar has a heap of apples. But I can remember that phrase a lot better for some reason than SOHCAHTOA. The only downfall I see to this phrase of SOHCAHTOA is I have to know how to spell it. And if I don't know how to spell it, then I don't have that ratio correct. And therefore, I might have the sides labeled wrong. So I like this phrase. But either one gets you to the point of being able to understand that all that sine, cosine, and tangent are is a ratio of 2 out of the 3 sides of a triangle. Again, and that's what we need to understand, is it's just a ratio, comparing one side of a triangle to another side of the triangle. This is asking for a specific type of ratio, either opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent. Okay, the next thing I want to talk about are two different types of reference triangles. One is a 45-45-90, and the second one we'll talk about is a 30-60-90. So if I draw my 45-45-90, what I know about that is this is my hypotenuse, and these two sides should be exactly the same because this is an isosceles triangle. So let's assign some specific values to that. Let's say that I say this side length is 1, which means this side length would be 1. Using Pythagorean theorem, I could then find this side of the triangle. 1 squared plus 1 squared would be the square root, or would be 2, and then take the square root of that, you get the square root of 2. So because I know these two sides, I can find the third side. So if I wanted you to actually find the sine of 45 degrees without using a calculator or using the unit circle, the question that you may be asking, or you may have wondered, is, you know, how did they get all of those sine, cosine, sine values that are on the unit circle that we talked about in the last section? Well, they're using the unit circle, or they're using these specific reference triangles here. So if I asked you to find the sine of a 45-degree angle without using the calculator or the unit circle, here's what you would do. I'm going to choose to go from this 45. You could go from that one. Wouldn't matter much. That would mean that this would be the opposite. This would be the hypotenuse, which I already labeled. And this would be the adjacent. Now remember, the sine is opposite over hypotenuse. So it would be a 1 over the square root of 2. And we'd have to rationalize that. So we'd multiply by the square root of 2 over the square root of 2. We'd end up with the square root of 2 over 2 when I simplify. And if I actually went to my unit circle and I looked at the 45-degree angle, I'd notice that it was giving me a coordinate point such as this. Square root of 2, or square root of 2 over 2, square root of 2 over 2. Again, remember, recognize that that's just a sine, cosine. And so the way that they were getting this was just using a right triangle trig. Okay? Let's talk about the other angles that are on the unit circle. There's a 30-degree angle, there's a 60-degree angle that is on the unit circle. So let's apply the same concept to a 30, 60, 90-degree triangle. So first thing I'm going to look at is this is a equilateral triangle, okay? Which means 60, 60, and 60. But if I was to take the time to draw an altitude in here, so I can get a right angle out of here, then now what I'm going to do is take and draw this triangle over here. That is specifically this triangle. So I've got my right angle. This is my 60-degree angle. This side... Actually, before I do this, I probably should have gone back to this for a second. Let me assign some side lengths for this equilateral triangle. I'm going to choose to do 2. And the reason I'm going to choose to write these as 2 is then when I put this altitude in here, it will bisect this, and this part will become 1, and this part will become 1. I specifically chose 2 so that when I divided it in half, I didn't get a decimal. I got a nice number to work with. So if I apply that over here, that means that this side was 1, this side was 2, this is then a 30-degree angle. I can figure that out 2 ways. This angle is bisected with that altitude for the equilateral triangle, or if that's 60 and this is 90, the only thing that I can have left for that is 30. So now I can actually figure out this side length by using Pythagorean theorem. This would have to be C for the hypotenuse, so it would be 2 squared equals 1 squared plus, let's just call that side B. And if you did some algebra, you'd find that it would be the square root of 3. So now if I wanted you to find the sine of 60 degrees, because it wants you to go from 60 degrees, you have to choose this angle. This is opposite, adjacent, and hypotenuse. So the sine of 60, the formula is opposite over hypotenuse. Square root of 3 over 2. Again, that is a unit that is on the unit circle. Again, and the way that they're getting that is they're just using this reference triangle. So I wanted to take some time to explain to you how those coordinate points came along from your unit circle. And if I ask you to to find sine, cosine, tangent of 45, 30, or 60 degrees without using the unit circle or the calculator, you have to draw these reference triangles. So let me kind of circle them for you so you know which ones I'm talking about. This is a 45, 45, 90 degree reference triangle, whereas this triangle is your 30, 60, 90 degree reference triangle. Okay, for this next problem, I want you to have your trig formula sheet out with you, or trig property sheet. I'm going to ask you to find the cosine and the tangent when we know the sine. So this is going to be two separate problems, so I'll do the cosine portion right here. Cosine. And then over here I'll do the tangent. Okay, so here's what I'm thinking. I want to look at my formula sheet, and if I'm trying to find cosine and I know sine, come up with an identity off of your formula sheet that will compare the two. Well, I know one of the formulas is that sine squared of theta plus cosine squared of theta should be equal to 1. That's a Pythagorean identity. Let's plug in what I know. I know that sine was 0.6, so if this is sine squared, it's got to be 0.6 squared. Cosine is what I'm trying to find, but I've got cosine squared. So let's go through and solve this. 0.6 squared is 0.36. Get rid of the 0.36 by subtracting. So now I've got cosine squared is equal to 0.64. And again, I want to know what the cosine is, right? So I get rid of the squared, and I'd find that the cosine would be equal to 0.8. So just by using this identity from my formula sheet, I can find the cosine. Now think about what I have. Now I have sine and I have cosine. So because I have both of those, if I want to try to find the tangent, use a formula from your formula sheet that compares, or that uses a cosine and a sine to find tangent. Well, I know one of the formulas on my formula sheet says that the tangent is equal to the sine divided by the cosine. So, to find the tangent, plug in the sine, which they gave us as 0.6, plug in the cosine, which we just calculated to be 0.8, divide that out, and you're going to get 0.75. Or if you'd prefer to write it as 3/4, you could do that. You could write this one as 4/5 if you wanted to leave your answers as fractions as opposed to decimals. I left it as a decimal because they originally gave me it as a decimal, and that's kind of a rule of thumb. If you find that your answer is a decimal, or that you're given a decimal, they typically want you to leave the answer as a decimal also. I'm not too particular about it unless I specifically say, you know, give answers as fractions or as decimals. Okay, we're still going to be looking at our formula sheet. This problem says, show that the left side equals the right side. So I already have my answer. This is the right side. This is what I want to try to reduce the left-hand side down to get to that. So as I look at this, I cannot move anything over to this side. I need to just look at this information. One of the identities that I know from my formula sheet is that cosine squared is equal to 1 minus sine squared. That's a Pythagorean identity, so I'm going to choose to leave the sine squared alone, but to change this cosine squared to 1 minus sine. And notice I'm putting it in parentheses because of the fact that I need to use the distributive property. Okay, if I don't put the parentheses there, I think I'm only subtracting the 1. So now what I'm ending up with is sine squared minus 1 plus sine squared. And if I combine my like terms, a sine squared plus another sine squared makes 2. And then minus 1. And so notice that this is exactly the same as that. At no point did I move anything away from the left-hand side over to the right-hand side. You can't move anything over. You need to specifically deal with what's on the left-hand side, figure out which identities from your trig property sheet you can make substitutions with. And again, I looked at my trig property sheet and I used this one, the Pythagorean identity, and I replaced it with cosine squared. And the reason I chose this identity was because I noticed there are no cosines over on this side. So I had to figure out how to get rid of that cosine squared. And I could do that with here. Mistakes that students will make is I want to move things over to that side. This is your answer. You need to figure out how to make the left-hand side mirror the right-hand side. So don't move anything over to the left hand, or from the left hand side to the right side.